Hello and welcome back. Today I have a multi-channel adjustable clock source, and this can be very useful if you want to connect non-standard equipment or older equipment to your laboratory reference. Not only has it its own OCXO, very stable source, it can also be connected to external reference, and that makes it very interesting. For instance, if you want to connect your Marconi, old one here, that needs 1 MHz, some of the HP equipment, especially the older ones, need 5, and the newer equipment, I did a modification on the Unity signal generator. The internal clock was 25 MHz, and also with these little oscillators or generators like this is based on the ADJ 4351. Also made the video for external reference, also 25 MHz. So then it would be great if you can do your GPSDO, which provides 10 MHz, use this one to create the 1 or the 5 or this 25. From the front we have a nice display, buttons to control it, which is very convenient. The color is different from the BG7 TBL. Also the size is just a fractional smaller, but that can come in handy, I'll show you later. But the height is also a fractional difference. And we have here a UART, that is TTL RS232. Here we have a USB-C connection, that is to power it, but also to communicate with the computer if you like. There is a little switch here. I think that is for programming if you want to change the source code. I don't think I will touch that. And here in the back we have the outputs, output 0, 1 and 2. And we have external reference in and a reference out. The internal OCXO can be adjusted, so let's see just how good it is. By default, you can see I already took out the screws from the top cover. There are 2 other screws below here, below this blue sticker, and then you also find there are a lot of pieces of plastic. First I thought the display is a bit unclear. There was 1 piece of plastic first, then I found another piece of plastic, and then below this sticker on top of the display itself there was another sticker. So removing those, we got a very clear display, so it's well protected. The UART connector in the front, I'm not sure what it is used for. Maybe if you like to program the source code. It is a STM32 module display. You find this in all forms and sizes. It's pre-programmed, so you don't need to do anything with it. If you like to communicate with the computer, I have the software. I will put that also in the download links. You should be able to communicate with it, but we use this only to power it, and the little switch there. So let's power it on. It does have an OCXO, so I like to see how long it takes to heat and to find it stable. It did not come with the manual, but it comes with this nicely, it seems proper USB cable. Only thing is you need to put it in the side like this to power it, so it sticks out. But you can find those 90 degrees USB cables that you can probably plug in, and then you plug it in like this, and then it is convenient that it is just a little bit smaller than the BG7 TBL devices, so you can get your cable out. But of course I would have preferred just a 12 volt in the back, and then yeah, maybe with a 5 volt linear regulator. That's probably what I will do. Because it is USB-C, I can just put in this little USB meter, and we can see how much current it will take, if it is stable or not. Well, we can see the USB is powered. We have a readout of the voltage, and it is kind of a soft switch, but it seems to work. I don't see any current flowing. Well, when we start it, it will go quite high. You can see it is sort of a soft start, and that is the OCXO. It will, well, we have here 700 millis. It will drop later when it's warm. Let's have a look at the display. While it's heating, let's go through the menu. It has 2 modes. This is mode 0. You switch it by long push to the top, and then it switches to mode 1. And again it switches to mode 0. Long push in the bottom will save your current setting as a default. We can see here it is running now on the internal clock. The clock is set to 10 MHz, which is the case. And then you have your first frequency that you set. And then you can say, okay, this frequency 0, I divide it by 1, and then I end up with this frequency. Then I divide this frequency with 5, and then I end up here with this frequency. So this way you can set several frequencies and all synced with your clock, internal or external. Also, you can do a little phase shift between this frequency and this frequency, or again the first frequency and the third frequency. The phase here I have set to 0, so I have a simple divide here. 50 MHz on the first one. The first divide is 1, so I end up with 50, and the second one is divided by 5, so I will end up here with 10. The other mode, somehow I cannot remember well. This mode has always been a bit confusing to me, but here I set a clock frequency. Here you have your first output. You can just set any frequency you like between 2K and 200 MHz. And then this frequency you start to do this dividing what you did with the other port. So if I set this one to 10, I divide here by 10, then I get here 1, and of course I have the phase shift. So this is one fixed port and one port you can adjust. So let's start to set it. Of course the clock is 10. If you use internal or external, doesn't matter. So we divide by setting first the frequency. Here, this one I want 10 MHz. So my first output goes to 10 MHz. Then I want my divide by 2. So here I have 5 for my HP equipment. And then I want my other divided by 10. So I have 1 MHz for my Marconi, and I don't need to phase shift. If I want to store that as a nice default, I just push long, and now it's stored. So when I switch it off and I switch it back on, it should be still there. Yes, we have a 10 MHz, 5 and 1. So first let's see, is the internal clock any good? We will be using the external clock anyway, but I like to see. So frequency counter is connected to the GPSDO, so how would it compare? I will just measure the output, so that means I will be measuring the internal clock. It's a bit loud, the signal. And well, we are below the hertz here. So it is not necessarily spot on compared to my GPSDO, but that is easy to adjust. Let's see what the frequency will say if we start using the external. Will it switch automatically? Then the readout should be better. So I will be connecting now the external reference. Here we go, connected to the GPSDO. We see here also it says external clock now. And yeah, it is now spot on. So that works. So it switches automatically while it's powered on. We can see it in the corner here, external clock. Let me take it out of the amplifier. Bloop, and then it switches back to internal. Put it back in. And it says external. So that works quite good. So out of the box, the 10 MHz is not exactly spot on, but yeah, it is within a hertz. So, but we can do that here. It is warm. I haven't seen the current change anymore. It's around 200 millis all the time. We should be able to do that in the back right here. We need to have a look at the frequency counter. That is up. It is a 10 turn, so it probably adjusts very easy. And it does. Let's get an extra digit. I'm going to use the faster frequency counter. That's easier to adjust. This one is like super fast. I would say this is pretty neat because here we have the hertzes, so we are here in the millihertzes. It's about as good as I can get it now. Looks like this one also agrees. No problems here. Internal seems fine. Now let's see what we did. So the first output should be 10 megahertz. So let's get that one first. That seems to work. We have here a near perfect 10. We are here in the micro, so that is good. Here also we have our 5 megahertz. The last digit is normal, that you will miss it. And here also our 1 megahertz also, all compared to the GPSDO. So this is nice. Now I set one output to 50 megahertz. The other one I divided by 2 to get 25 for the Unity like devices or that little generator, and the other one I divided by 5 also from my F0 divided to get 10. What we have, a nice 50, this is micros, 25 and a nice 10. So that's pretty cool actually. I want to use this instead of my PLL. Let me show you why. Well, I already have a device like that, and that is this one. This is a 6-port PLL, BG7 TBL. I built it in a casing myself. I have a few videos about this, and I used it also for the Unity generator because it needed 25 megahertz. The downside using that PLL here, it works great, but I always need the computer, and it works with an old serial port, so I need a converter for that, and the software is kind of old. So I always need to use my computer for this, and with this new device I can just control it completely in the display. You probably saw me that I already removed the screw, so let's have a look inside. So removing the 2 screws behind the sticker, removing the screw here and here, and then we can open. Not a surprise, they're using the Vector or the CTI in this case. 5-volt square wave, nice overniced. You can find these cheaply in AliExpress, mostly second-hand from old phone towers. I did a video on those with schematics of everything. This is the CTI, I have the Vector on here, and also the Trimble. I can leave those documents also down below. So what is it all based on? Well, this is these STM32 devices with a display connected to it. I think it can communicate with RS232 or I2C, and I think in this case it is I2C. When we look here, well, this just looks like a regulator here. This is usually a coil, so this is the power to get a nice stable power. This could be buffer right here. The 3 outputs, well, of course, here is the 10 trim pot, well, goes directly to the OCXO, no surprise there. Here it goes to the 3 outputs. Well, this seems buffer, buffer, buffer. And here, this is probably the main one. Let me try to zoom in on that. And of course here, this is probably just a switch between internal reference and external reference. They detect here if a signal comes in, then you flip the switch and you put it out, and that's about it. And probably there is somewhere a signal line communicating back to the display that it is running on external. Let me make some photos with the microscope and have a better look. Here we have the board closer by. We can see some Chinese text that I will try to translate. Has been some work done here. I will try to clean that up later. Yeah, when we have a look here, clearly this is the power line for the OCXO. This line just goes to the pot here, so that is the control voltage. Then the signal goes out here. This seems like a DC decoupling, DC block. And then this is probably a buffer to get the signal out to the external output or out here through this device. And what is this? Use the Google Lens function of the Google Translate to find out what it actually said. And it came up with this, which means a multi-channel clock source external clock selection output with driver stage. Okay, so that's clear that those are probably drivers. Well, let's zoom in on this one. After we clean up, it looks like this. But this is a 53501. It took me a while to find it, but I did. And it turned out to be the Si5351, which is a programmable frequency CMOS clock generator. And that is exactly what we need here. And it is programmable with I2C. And I see here highly linear VCXO. Optional clock input, which is now important, of course, and it can go from 8K to 160 megahertz. But I found if you buy it from another brand, it says it goes from 2.5 all the way up to 200. But then it's also in different packages, but I think we are looking at this one here. Here we have an OCXO input, we have the I2C interface input, and we have our 3 clock outputs. Let's put this block over our PCB. I put the picture and the block exactly in the same orientation, and we can clearly see this is indeed what it is. We have the oscillator input on the top, these 2 pins here. Well, here we have that. The I2C here goes to the front display. We have that here. And our outputs, here we have it. And then these buffers, let's have a closer look to those. Zoomed in 7Z25D turns out to be this one from onsemi. It's a buffer indeed, and what can it do? It is even tri-state, but it can operate also in the way it does now. And I think here we can drive here at 24 milliamps, so that is a proper buffer for these type of signals. I think it was around 2 point something nanoseconds, which again is around this 117 megahertz, so close to 200. And we have the internal external switch area here, and well, that's a very common 74HDO4. And then we have the power circuit. Well, here we already saw the coil to make to remove all the RF signal from the power, and here we have, yeah, sort of a regulator, I would think. I did zoom in here with the microscope, and it says 19GP Ti, and that turned out to be this one. And this type is here the TPS 78910, and that is indeed a high accuracy, low noise voltage regulator. And it can also do current limiting, but it can also switch on and off the OCXO. When we look at that regulator, we see here also there is an enable pin here, and you can switch on and off the output power. So they could have switched on and off the OCXO when you're using external reference, but they did not do that. They just connected the enable line to the import. Because when we look here, this is the enable pin, it is here directly connected to the, there is a bridge in the bottom of the PCB to this import. So if I want to switch it on and off, so I could use this signal here, connect this to the 7404 that we have on the input part of the external reference, and then I could actually switch off the whole OCXO automatically just based on the signal from the 7404. And then of course the display module. Well, we have the USB port here. It is used to power and to communicate with USB with the software if we use it. This switch is kind of unclear to me. I would think it is to set it in some sort of program mode so we can update the source code. And here we have the UARTTL, so we need here a TTL to USB converter to actually start programming the STM32. That cable here goes to the display module and to the buttons. And here this flat cable here I removed for the picture goes here to the main board below. It powers here the circuit for the OCXO, and on this side for all the buffers. And of course the 5351 and 2 other pins will be used to connect to the 5351 with the I2C. I must say I like the effort they put into giving clean power to the OCXO, also keeping the current in control. Probably also because they use 2 tiny of these flat cable wires to power it all, and it can take around 600-700 milliamps. So probably that is one reason they did this, but also to keep the signal clean, and also with the big coil to get all the RF out. So they've done a great job also here with the buffers, 24 milliamps. So, and it's probably also protected for short circuiting. So they did a lot of things. So it looked pretty nicely built. When we look at the teardown, will it do up to 200 megahertz? I am not sure. We already saw that some of the components are really, they specify 170. So maybe pushing it to 200, just the signal will probably go a little bit down with it. Well, I think it will still work. But the main thing is we probably use it between 1 megahertz to 50 maybe at the most if we use it indeed as a clock reference. So that is all fine. I will add also a screenshot of the software. I myself are totally not interested in the software at all to control everything, because the whole point was for me, I can control it now through the display because I already have a PLL here that I need to control with the software. But I will add a screenshot. The seller will just, when you buy this on AliExpress, at least the seller that sold it to me, I just sent an email, can you send me the software? And he did immediately, no problems at all. There is one modification I like to do. It almost would have been perfect if it had a DC 12 volt plug in the back, because now I need to modify it. I don't like a 90 degrees USB going to the back, and then I have my USB cable, and then I still need to use some switch mode supply, and I have everything here on 12 volts linear. So I would like to do that just with a simple analog regulator. It's 600 when it's starting up, and then it goes down 300, 400 milliamps. I don't expect any problems with heat. So that's it. Thank you for watching. I hope to see you next time.